So today I think it's time to introduce another language to this course. And the language is Fortran, which is a language that is older than myself. So it's from the 50s, 60s, the original versions. In this course, we are going to focus on the modern versions of this language. So I'm not going to go through a lot of things from the Fortran 77 standard or older. So we will focus on Fortran 90 and above, which is a really different language from the original ones. So first, a little bit about history, because this is, as I said, a very old language. So the first version of Fortran appeared already in 1954 as a response to before, in this age, many of the supercomputers or large mainframes were programmed in machine code or assembler, down to the metal. And that was hard to kind of, when they bought a new computer, you had to kind of rewrite all your code. So Fortran was a response for providing a way of writing formulas and code in a higher level language. It has also been standardized, so international standard for many years. So there has been multiple standards of Fortran. So the first one was actually Fortran 66. Then we have Fortran 77. And then we have a major upgrade to the language in Fortran 90. But it's still completely backwards compatible, which is important. There has also been an interlude here with something called the F programming language, where they try to remove all the backwards compatibility stuff to make it really stand out, but nobody really used it because backwards compatibility is something that is important. There was a minor update here, Fortran 95, which removed some really ancient stuff in the standard, but no, basically it was Fortran 90 with some bug fixes. Then we have Fortran 2023, which is a major update where they start introducing object-oriented stuff into the language. And there is a Fortran 2018, or I'm not sure if it was released then, but I think the numbers here will change. But it's continuous developing language, even if it has many years. It has a very long history. So I just want to show some code here to compare Fortran to other languages. So this is a Pascal program for calculating something here. You can see here that you have keywords for the program. There's a begin, end here. There's a function definition here. So it contains a lot of the modern stuff from many modern languages. C looks like this. You don't have begin, end, but you have curly braces instead. You can define functions here using F. There's a main function here. And you have if statements and for statements like this. So if you continue on to the first version of Fortran, just to kind of compare. So this is the 50s version of Fortran. But you can still see here, I mean, compared to machine code, this was a significant step in how you code for computers. Because you have to go to machine code. But there are stuff like this here. So you can see you have row numbers here. And a do loop, you have to specify that the starting point of the do loop, where it repeats, and so on. And you also have to specify, of course, the range here. But this here was revolutionized. You can actually write scientific formulas using expression in text. This had to be hard-coded before in machine code. So this was a significant step up. Same thing here, we have if statements here. So if true, go to 8, otherwise go to 4. And you have go to statements here as well, and stop statements. Kind of primitive, but still a revolutionary step forward in scientific computing. Then we have Fortran 1. They added stuff. You can define a function. You can define format statements here for formatting outputs. So you see, we work in Python for format statements. Fortran had that really long time ago. Now you have to specify one. Instead of, so where it repeats the do loop, you have to specify a row number here. So here, continue. This is the do, continue. So you have to specify this statement here for this number, for this row. You can also see here that it has a very strict source code formatting. So you have all the statements here in a single column. Then there is a C here for the comments, which is in the first column. And then you have line numbers here. And that is actually for it. It was assigned for punch cards. So the formatting of source code is actually from that age. So you have to be kind of strict where you put stuff in the source code. Then you can see here it evolves over time here. Fortran 7.7, this is the first modern standardized version of Fortran. So here you can see that you still have the looping statements here, but you have if, then, else, and if, which is, so you don't have to do any line numbers for if statements. That was kind of a big thing here in the Fortran 7.7 stuff. And this language, there are still code that uses code from this era. Then we jump forward in time, and you can see here that now all the line numbers, or the line numbers are gone. We don't have a fixed format source code anymore, so we have this. You can write code wherever you want. You can indent if you want. There's no line numbers for things. There's also, you can now express it where you're declaring variables. So a lot of new stuff. You can also see that you have end program here, which is very similar to what you have in Pascal. Yeah, I will go into more details later here. So this was kind of a comparison with the different languages and how far Fortran has come. So as I said before, Fortran 7.7 used fixed format source code. That means that code in position 7 to 72 are statements. And then the line numbers in position 2 to 5, you have a comment at position 1, characters position 6 for continuation, only one statement per row. And Fortran 90 remove all these restrictions, most of them. So you still have, so it increased the number of characters per line. So you can have max 132 characters per line in the standard. So most compilers today accept longer lines, but if you want to follow the standard completely, you should limit yourself to 132 characters per line. Comments, you can place an exclamation mark anywhere on the line, and that text after that will be a comment. You can continue with an and at the end of the line and continue the next line. You can have multiple statements per line by using a semicolon between the statements. So basically, with Fortran 90, you got a language with a modern way of writing the code. So here is an example here. So you have program example. Implicit none, I will come to that later, but because of compatibility in Fortran 77, you actually didn't have to declare variables. So all variables I to n was declared integer by default, and all other ones were real. So that can kind of confuse a lot of things and also introduce a lot of errors. So in Fortran 90, they added a declaration here called implicit none. That means that it tells the compiler everything has to be declared. No implicit rules. And that means that all the variables and constants has to be declared with the data type. So here you can see you have this is a constant here, a parameter that means that it's a constant, it's an integer. You have real here, that is a floating point variable. And this is a position specifier, which I will also come to later. You can declare two-dimensional arrays using variable name and then the dimensions. This is a comment. These are continuation statements here. And here you can see here, write, semicolon, write, to have two statements on single line. And this is the default here. And then you can call a subroutine using the call method here. Stop is stops the execution of the code. And then you have end programs. So stop is not strictly required. When it comes to end here, it will stop the code anywhere. But this can be used with return codes as well in different parts of the program. The main program structure of a Fortran 90 program is, there should be an explanation here. So you start with a program and then you define a name of your program. You have specification statements and you have executable statements. You have contain sections and then you have subroutines. And then you have end program, program name. So this is if you have in a single source code file, you need to have these parts to build up the program. You can have multiple source code files, but the main program looks like this. And also something you have to remember now when you come from Python or others or C++ is that variable declarations goes before executable statements. So you can't declare a variable in the middle of your code. You need to declare it in the beginning of a subroutine, beginning of a program, beginning of a module, and so on. So the ordering is important here. Subroutines here is very good to subroutines if you are subroutines in a single source code file. We can see here that the brackets here denotes that it's optional. The only thing that you need actually to have in a Fortran program is end statement. So the smallest Fortran program you can write is 3 letters, end. It's done. But you need to have end. So just to get you started to how you compile and run your Fortran code, Fortran is not an interpreted language like Python. So it's not a scripting language. It will take your source code and compile it to machine code, which you execute on your machine. And just go through quickly how to do that. So executable code, it's also equivalent to machine code. It contains machine code. And so it also contains links to system libraries that you use that requires to run the program. And you can also have some external libraries as well. So system libraries are the libraries provided by the operating system. And external libraries could be, for example, math libraries, solution libraries for different things. And you combine these together, you create a program. So you can create programs in different ways. The hard way is actually to hand code and machine code, basically entering the numbers of an Intel compilers, the different statements in numeric form, which is really, really hard. If you go one step up, you can write something called assembler source code. That is where you have all the machine code instruction in pseudo names that you can use. And then you compile that source code to machine code, which is not so hard. Or you can use Fortran C or C++, where you use you take your source code here and you compile that source code to machine code, which is easier. And then finally, we have Python here, Python program that compiles and executes each line when you run the code. So how do you make an executable? You write your source code. And then the second step is you compile the source code to object files. And object files are unlinked machine code. So those are, your code has been translated to machine code, but the calls to other statements here are not linked to an actual address. And the final step, you link your objects together with your files and the libraries to make up an executable. So on Windows, usually an executable is an .exe file. On Linux, there is no extension, but usually there is the executable bit set. And on Mac, it's the same thing. It's also similar to Linux. So the procedure looks like this. You have your source code files here. The compiler compiles the source code file to an object file here. Every source code file becomes an object file. We have libraries here that are pre-linked object files. And then finally, the linker links together these files here into an executable. And this executable has no connection to the source code. It's completely independent. It's just machine code. It has dependency on the system libraries here. If you use dynamic linking, it will load libraries when it runs. You can also create an executable that has static libraries. Then it has no basic dependency on the system except for the standard C libraries. So how do we do it practically? So if you are on a Linux system, you can, for example, load a module called FOSS, which is free and open source software compiler suite for 2019. There is a 2022 now as well. So, and when you load that, you get, there's a lot of modules loaded here, but the important thing is the GCC core here, which is the compiler module. And then you should have a command called Fortran that you can type in your terminal. And if you put version here, you can see what version of Fortran you have as well. We are now at 11.2, I think, in the compiler versions here. So if you want to compile, you can write source code, use the F90 extension. Then it will use the compiler would expect a free-form source code file. You can compile an object file using the following command. So JFortran for the calling the compiler, -C for compile, mysource.f90. That will produce an object file called mysource.o with an unlinked machine code. You can use multiple source code files, JFort -C source 1 and then source 2. And that will create two object files at the same time. Linking Fortran source code, JFortran mysource.o, that will create an executable. As there is no name here, it will be by default called a.out, which is a standard executable produced by compiler if you don't specify a name. So if you want to have a specific name of your executable, you can add a .o here, for example, for myexec. And that will generate a myexec executable on a Linux machine. On a Windows machine, it will .exe. But fortunately, the JFortran compiler can do this in a single step. So if you have a source code file, you can type JFortran mysource.f90 -o myexec. That will compile an object file and link an executable in a single step. So this is the easiest way to compile a Fortran code is using JFortran source code file and myexec. And you can also do mysource1 and list all your source code file in a single line and -o myexec. So that is just how to get started with compiling. And I will provide links where you can download all the tools that you need. If you have access to Lunar, you just load a module and you get the Fortran compiler. So coming back to the language again. So important concept is to declare variables. And in Fortran, in a variables can be from 1 to 31 characters long. They can contain letters, numbers, and underscore. You can have multiple, both uppercase and lowercase in the characters. But important is that variables are case insensitive. So A and small a is equivalent. So they refer to the same variable. Python is case sensitive. Fortran is case insensitive. And also first character can't be a number. So if you look here, we have value variable A, because it's a single character, starts with a letter. Anything, that's also okay, starts with a letter, there's an underscore, okay. X1 as well, mass, Q123 is okay, time of flight. This is not okay, number can't start with a number, can't contain space, and you can't have an underscore in the beginning. So you can't hide variables like in Python with underscores. The primitive types that are built in, you have integers, real, complex, logical, and character. Those are the main primitive data types that are built in. Then you can, from these data types, you can create arrays, your custom derived data types that can consist of these primitive types. You declare a variable like this. You have the type here is the first. So, for example, real integer. Then you have a double colon, and then the variables that you want to declare of that type. Here you can also have an optional part that can specify additional attributes of your variables. So, for example, if you want to declare a constant, you can have type, so real, parameter, colon, and name. Then it becomes a constant. And there are some other ones that we will go through later. Then you specify those before the double colon here. So here are some examples here. So declaring a single integer, double colon, 8. Real, this is a single precision real, double colon, b. Logical, same thing here, so that's a Boolean variable. Array of 10 elements. You specify the data type, variable name, and then the number of elements in your array. Two-dimensional array, data type, variable name, and then the dimensions here. There is a different way of declaring arrays. So we can use attributes here to declare integer dimension 10, colon C. So C will there be an array of 10 elements. The advantage of this here is that you can declare C, D, E, E, F, and all of them will have the dimension 10. You can declare a character. So this is a single character. You can declare a character dimension 60. You declare an array of characters. If you want to declare strings, which is not the same thing in Fortran as an array of characters, instead of declaring it dimension here or after here, you declare a character, length equals 80, then you get an 80 character long string called line. If you declare like this, character length 80, line 60, then you get an array of strings of the size of 80. Also, just to note that Fortran is not very good at string manipulation, so Python is much better to do strings. So if you do a program where you mix languages, do all the string manipulation in Python. You can do it in Fortran, but it's more complicated. Constants, that is variables that don't change during execution of the code. You can also not change them. You add this parameter here to the attribute list. And then A here will be constant 5 during the lifetime of your code execution. You can also use constants here when you declare variables here. So this will be a C is an array of 5 elements. So the declaration you saw before just declared the variables as the least precision by default. But you can add precision to the variables by adding a parameter to the declaration. And the thing is that with Fortran, this is an old language, and the standard doesn't specify the exact data type of what this precision means. So the precision specifiers are dependent on the compiler and the system architecture. But to save us from making mistakes, there are special directives in the language to query for a certain precision in your code. So if you want a certain precision, you can query the compiler, give me a constant that corresponds to that. And those two directives you can use is selected real kind and selected in kind. Both of these return values and are not the normal functions in Fortran. They are in compile time. These will return certain value that you can use for declaring the precision. So here, for example, you can have explicit precision specifiers. Real parentheses 8. That means this is the precision specifier. Then you have real 4. That is also less here. General. If you are an Intel platform, which most of us are, these are real 8 means 8 bytes for a floating point. This means 4 bytes per floating point, which is equivalent to the float in C. And this is double in C. Integer 4 is the normal integer in C, and so on. But this is not, it's not guaranteed. So if, for example, if you run on really exotic hardware, those numbers here can differ. It will compile, but it's not always what you want. So you need some way of querying that in a system-independent way. So what you can do then is you can use this selected real time here. And you see how many decimal precision you want and how the exponent mantissa should be here as well. So you call this here, 80 will be assigned to a value. This is a constant here, must be a constant. Then you use this constant here when you declare your variables. So this is the significant decimals here, and this means that you have you can represent 10 to minus 300 up to 10 to 300. You can also declare, if you declare a scalar in your source code, you can also specify the position here by using a postfix here called essentially underscore RK. This is the position specifier that you declare uses the read time. This tells the compiler this scalar should be represented with this position. If you don't do that, Fortran kind of reverts to 50s thinking. So in the 50s, storage was precious. You didn't want to store scalars with a too high precision. So if you remove this part here, it will store it in single precision by default, so take up less space. So somehow, so that is also backward compatible to old Fortran. That by default, if you don't specify, it uses the lowest precision. So this is an example of this. You have I have 2 pi's here, 2 variables, pi1, pi2. I have created selected real time 15,300 here. And I assign a scalar value to the pi1 with all the decimal points of pi. And the second one here I call 3 point, same thing, but I add the precision specifier here. And just write them out to the screen. And you can see here that this one here loses the decimal points here at 59274. It's not the same. So it's half of the value here. And then the one that is declared with precision here stores all the decimal points, so decimal values. So this is something, a common mistake in Fortran code is that you don't specify this precision here. Specify. If you do this, you lose precision of a scalar value that you have in your source code. So this is important here. There are some compiler directories that can force declaration of all your variables, but that is not part of the standard. So if somebody takes this code and compiles over a different compiler, different options, you will lose precision here. I alluded to this before that by default, there is something called the general type rule. So by default, variables does not have to be declared in Fortran. So it's almost like Python. General type is defined. So variables starting with I to n are by default integer, and other variables are real by default. So if you look at old Fortran code, you can often see this, that I, j, k, l, m, n usually used in loops for loop variables, and variables with a and higher you can are real. So, but this is a problem that if you don't do something about it, you can declare variables without thinking, and then there is a variable that's not declared, but the code compiles, but it produces strange results. And that is usually due to the general type rule being in effect. That is, okay, here's an unknown variable, oh, then it's probably integer or real. But you can place implicit none and take that as a advice. Do that for everything you declare in Fortran. So try to have implicit none here, forcing you to declare every variable. So if you have implicit none and there's a variable not declared, the compilation fails. So this is a good rule to use. You assign variables. They use the equal sign here. I've already shown it several times. So this is a precision specifier. If you have logical Boolean variables, there is predefined operator to use. So dot false here you can use to assign a false value to a logical value, and dot true. Characters are assigned using the single episode or double quotes here, like this, just like in Python. But strings in Python in Fortran are not dynamic. So if you have a string that is long, it will still have characters after here. So it's not like you can add strings together in an easy way, because the strings are always fixed in size. Also, declaring a variable and not assigning it is perfectly okay. It works, but it's considered undefined. And you should never use undefined variables because you never know what they contain. So in Python, floating point value is predetermined to 0. But in Fortran, this will declare a variable that has memory location. By not assigning it, the value of that variable will be the value in that memory location. So it can be a garbage value, or it could be 0 or anything. So it's very important that you assign them. And when you have assigned a variable, it's considered defined and not undefined anymore. And now it should be able to reference by other expressions. And also, if you have an array, it's said to be defined when all array elements has been assigned. Otherwise, it's undefined, even if you assign a single one. There is nothing that prevents you from using undefined variables, but it's dangerous, and it leads also to many errors. Derived data types is a special form of variable that you can define yourself. And they can contain standard variable types, arrays, and other derived data types. And you derive a new data type using the type statements and listing the members of that derived data type. So it's very similar to redefining a class in Python, but this is just for data. And then you can use this variable type just like any other variable in your code. So you do type here, and then your name of your newly defined data type and a variable. So here's an example here. I have a particle here with this one usually contains the precision here, so I put it here. But I have 4 members here: X, Y, Z, and M for math, for example. And then you n-type particle. So now I define my derived data type called particle. Now I can declare a particle using type particle P. And now I can use P for percentage X equals to value. So this is the same, corresponds to the dot operator in Python. So %Y, %Z, and I can assign them individually. And I can print them out like this as well. So I don't know why they didn't have the point operator here. Probably because they haven't any other character. We couldn't use the dot because it meant something else. So this is a way of declaring your own data types. And of course, you can mix here as well. So you can have any kind of data type in an array data type. So you have real integer, logical, and character string. So we can combine them into a single data record from an address list or something. Operators. So these are the standard operators in Fortran. You have double power 2, it's 2 stars, multiplication, division, plus, and addition, subtraction. Order is parentheses, power operator, multiplication or division, plus and minus. Yeah, it's equivalent to other languages. You also have relational operators for use in Boolean expression and if statements. So you have less than, equal to, greater than, equal to, not equal to. There is also an older version here with just ASCII codes here. So .lt for less than, less equal, which is still can still be used in Fortran 90, but I recommend using the modern ones. You also have the logical operators .and, .or, .not, which can be used in your if statements as well. Integer statements will be truncated down to 0. So here 6 by 3 is 2, 8 by 3 is 2, minus 3 is minus 2 here. Yeah, as I said, because it's integer division here, this will not work here. You need to go to floating point for this to work. Also, if you have different data types in a single expression, so if this here b is a real variable, if you multiply a times I here will be converted automatically to a real. So it will convert to the highest, to the first to the stronger type. So integer is considered weaker than real, then I will convert it to real as a stronger type. And the result will also be a stronger type. Also, all the operations that you have for operators can be applied to arrays. So this is something that was introduced in Fortran 90, the possibility to use, to work with arrays as a data structure. You can add, subtract, multiply. The only thing that you need to check is that you have to have the arrays that you multiply or work with should have the same size. If you have scalar values, they will be distributed to all the elements in the array. So if you multiply with a scalar, that scalar value will be multiplied on all the arrays. Also, order array operation is not specified in the standard. So that is the reason for that is to be able to enable efficient execution in parallel machines as well. So just an example here. So I have three variables. I have two-dimensional arrays, A and B, one-dimensional array, B. If you do A divided by B, that means that elements Aij will be divided by Bij. That will be done automatically. You don't have to loop here. You can just use our expressions. If you do B plus 1, this is a scalar, so that will be added to each element in B. Same thing here, 5 divided by B, that's division here will be every value in 5 will be divided by B. And then you have A 1 to 5, so you can use index notation, I will come back to that later as well, to extract 5 elements of A and add that together. You can also do A equals B, that means it does a comparison of all values in A compared to B. If they are the same, it returns true, otherwise it returns false. So these are quite powerful. You don't have to do any looping for doing stuff like that. This is built into Fortran. So we come automatically to the array matrix section here. We already seen that we can do arrays in Fortran, and it's very efficient data type in Fortran. You can allocate them statically, which we have seen before. You specify a fixed size, 20 by 20, or you can allocate them dynamically, which we'll also show later here. Fortran also supports advanced indexing, slicing, and assignment. So if you're used to MATLAB or Python for indexing, you can do many of these things in Fortran as well. It's also possible actually to redefine the indexes of an array. So by default, arrays in Fortran starts with index 1. So here's one thing that differs from Python, but you can redefine them using this syntax here. So index -3 to 3. That is, these are the indexes here, -3 to 3. So it's possible to redefine them, but by default they start at 1. You can assign individual element by specifying the rows and columns, and then assigning a value. But you can also do stuff like this. This is a 2-dimensional array. assign 5.0, it will assign all values to all array elements to value 5.0. So no looping to initialize variables. However, my friend at Lunark, he always warns me of, do not do this just to zero things out. If you are going to read an array, fill it completely out. There's no need to zero it before you read and assign. Because this operation, if you have a million by million array, it's a long operation. So if you are going to read data into an array, don't zero it out just because you need to zero it out, or just because you want to be safe. So if you assign all elements, you don't have to do this. But if you need a zero array, this is the way to go. You can also assign, if you have a 5-element array here, you can assign the values in a single row here. You don't have to do multiple assignments. You can do parentheses slash, and then you just give the values here with comma separated. Very similar to how you assign a list in Python, except you have to do this here in the beginning and this in the end. You can also, in this case, you have a 4x4 array here, and 4 one-dimensional array 4, and same thing with C. You can assign B here by selecting the row and then all the columns. So this means that this is row 2, assigns B to row 2 or A. You assign the values, the C of the values of column 1 in A to all the rows in column 1. You can also assign slices like this. So you can have an array here of 5 by 5. You can do all the columns here. So this is the row 5, and here's the values for row 5. And here you can also add, that's the same thing I showed before. So assign the array values 5 for something that it's important to understand is how things are stored. I think I comment this in NumPy as well. So arrays, regardless of dimensions, are always stored in continuous in memory. So all the values in the entire array is stored like a single array, one-dimensional array. And two-dimensional arrays in Fortran are stored column-wise. In Python, they are stored row-wise. So just to explain here, so if you have a 16-element array stored like this in memory, it's kind of natural. But if you have an array that's 8 by 2, in Fortran it's stored 1, 2, 3, 4, 5, 6, 7, 8, and then it goes up here 9, 10, 11, 12, 13, 14, 15, 16. So these are storage location in memory. And if you have 2 by 8, they are stored like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. This becomes important when you want to connect Fortran and Python together. Then you need to make sure that Python allocates the arrays according to the right storage scheme. So and that is possible. I will come to that when we go to mixed language, but that means that you have to tell Python when you create an array that you add an F here for specifying I want a Fortran array. Okay, I didn't already do that. Okay. But that was a bit about arrays, conditional statements. If statements, the simplest form is if, parenthesis, expression here, execute. So if this expression is true, this statement is executed. That is the smallest form of this statement. Then you can do if and an expression, then this code block will be executed if this is true, and if. So in Fortran, there is the code structure is not, that doesn't define the code blocks that you need to do then and if that defines the code block. You can also do if expression here, if that is true, you do this. Otherwise, if this is true, do this block, otherwise do this block. So here's an example here. I have a new statement here. So if x greater than 1,000, it will execute this one here. If x less than equal to this one, and then if you have if flag, so if you have a Boolean variable, you can just put in the variable name like this, and if it's true, it will be this part of the executable. Otherwise, this will be off. There's another form of if statement or way of selecting selecting things depending on the different condition, and it's called select statement. It's similar to what you have in C called switch. So you have an expression here, something you would evaluate, and if that is this value here, it will execute this block. And you can list them, several of these here in a single select case statement. And then if nothing is fulfilled here, it will execute this default section. So this is an optional part you can have as well. So here's an example here. You have value here. You enter the value. Select case, if the value is greater than 1, this is number 1. You can see it's also 2 to 9. 10, 11 to 41. So you can actually set a certain criteria here as well. And if nothing of these are fulfilled, this one is executed. So we will make a 10-minute break and we continue after that. Okay. Okay, I will repeat again. We'll get back, sorry. quick recap. Repetitive statements. We have the do loop, starting value, end value. This is the loop block. There's a second version here with a step parameter here and the loop block. There's a second one here. Oh, sorry. You can also, inside your loop, you can exit the loop. You can terminate the iteration and go to the statement after the end statement. Then you have a cycle to continue to the next iteration of the loop. Then you also have a second one called with the do while, where you can have an expression, and if that expression is true, the block here will reiterate. This one we have to be a bit careful about, because if you don't check all this, it can go into an endless loop. So you need to have some kind of reasonable termination expression here. And here an example of this. So do while x is less than 1.05. Start with a value here, and then I continue here until x is not this one here. So you can see I update this x here all the time. If I don't do this, it will kind of continue forever. Runtime library, so built-in functions, mathematical functions. These are the standard ones, and all of these functions work on arrays as well. So if you give them an array, it will calculate these functions on all elements in the array. Here are some conversion functions. The absolute value of a, try and take the floating value into and also int here to convert to a different data type. Rounds the floating value to the nearest integer. Also, this one here real converts an integer to a floating point. So it's similar to what you do with float parentheses in Python or int parentheses in Python. There's a max function here that can return a maximum value of 2 or more values. Same thing in here. You can have a list of values, list of variables, and it will return max or min on that. There are some vector and matrix functions that work on arrays. So you have dot product, return the scalar product of the two vectors here. You have matmul, which is matrix multiplication. So the normal multiplication operator in Fortran is element-wise multiplication. So it's similar to what you have in NumPy. But here, matmul, this is matrix multiplication that is built into Fortran. So you also have to check if you assign another array here, it has to be the shape of the resulting matrix multiplication. Otherwise, you get segmentation faults, or your program will crash. So it's not as flexible as NumPy arrays where they automatically resize and stuff like that. This is, you need to know the sizes of everything. Transpose C will return the transpose of C. Here are some examples here. So this is A divided by B. This is array, and array. Then you have this division here. Each element in A will be divided by the corresponding element in B. C here will be an array calculated from the square root of every element in A. So I will do a bit larger example here. So this is mechanics. This is a calculated stiffness matrix for a very simple element, bar element. We have these matrices here. So we have G transpose multiplied by K element here, multiplied by the J matrix here. So J is like this. This is the stiffness matrix here. These are scalar values calculated here. These Nx, Y, Z are defined here. So if you want to do this in Fortran code, you do it like this. First, I define all my variables here. So I have a 2x2 stiffness matrix, 6x6 global matrix, and the J matrix is 2x6. Assign all my scalar values here. You see that I use the position identifier here, RK on each of these, to make sure that these are actually represented with the highest position. Then I calculate the length scalar here, and x and y and z. Then I define KEL using row by row. So instead of defining in a single, I do it in 2 steps here. So the first row here, I assign 1, -1, row 2, -1, 1. And then I can add my scalar constants here just by doing KEL equals to KEL multiplied by this one. So this will multiply all elements in the array with this evaluation of these 3 scalar variables. Then I do the same thing with J here. So the first row of J is equals to this. Second row equal to this. So then I can kind of see to read the code instead of having it in the list like this. Then I calculate the global stiffness matrix here. Here it's not as easy to do expressions like in Python. So I start with this inner multiplications here, transpose J times KEL, and then I multiply this one here with J and outside here. So you have to kind of nest them together here to get multiplication. But there's no looping required. So this is kind of implemented in Fortran itself. And I just print out the contents of KE. So this is how you can convert matrices to code. So it's a bit more complicated than MATLAB, and it's a bit more complicated in Python, but it's still similar to how you handle arrays in Python and MATLAB. The only difference is that you need to declare all your variables here at the beginning. Also, that you have to declare all the sizes. There is no automatic allocation here. You need to do all that yourself. So it's a bit more manual. And if you run this, you get this here. And it should be a symmetric matrix like this. So next, we want to divide up our programs in more manageable sizes. So defining modules and subroutines to kind of make it easier to implement your code. So as I said before, you have the main program. It can only be a single main program in any Fortran code. So this part here can only exist in one of the source code files of your Fortran project. So you can't have multiple program statements in a project. And this one signals the end of a program. Also something about the stop. So stop the program execution. And you can call that in any subroutine you have, and it will terminate the program. And I think my principle when I design Fortran code is to do not call stop unless it's really extremely important to stop the code. So try to return an error statement back to the main program and handle errors in the main program instead of crashing inside a subroutine. You can also have stop statements that can have stop codes, numbers or strings that will return back to the operating system. Okay. I think that code has to have stop routines in subroutines and functions. So if you have an error condition in your subroutine, return back to the main program and handle the error there and terminate in a somehow controlled fashion. So subroutines. So now it's getting a bit more complicated than you have in Python. You can have, there are different kinds of subroutines in Fortran. You have external subroutines. Those are placed in separate source code files that have an implicit interface, and they can be implemented in many languages. So basically, it's you compile source code files and you get object files and you link it together separately. Internal subroutines, there are subroutines contained inside program units. And they can also be in modules that will come to later. So you can have a module subroutine inside as well. But so internal subroutines inside program units, so in this contain section here, this is internal subroutine. And you can actually have internal subroutines inside a subroutine as well. So you can have things that you don't want to expose, you can put inside a contain section in the subroutine. So all units in Fortran code can have internal subroutines. And then you have module subroutines that are subroutines that are contained in a module. So subroutine in Fortran has the following suite. You have this subroutine keyword, the name of the subroutine, and then you have a dummy argument list. And the dummy argument list is called a dummy argument because these corresponds to, can have any names and corresponds to the variables coming into the subroutine. And the next step, you declare all the dummy arguments and also the variables used inside the subroutine. Then you have return, just like in Python, to exit out of the subroutine, and then end subroutine name. So the name here at the end is optional, but I think it's a good idea to add a name or a subroutine when we end here as well. Then you can see in the code that this belongs to a certain subroutine. Variables passed to subroutine always passed by reference. That means that the variable in the call subroutine with a variable inside a subroutine, that is a reference to the actual variable outside a subroutine. So if you modify a variable inside a subroutine, it also modifies the value of the variable in the main routine, for example. You need to declare the arguments inside a subroutine. And then if you want to execute or call a subroutine, you use the call statement. And then you return with the return statement. You can have several return statements in a subroutine, so you can return from multiple places. So here's the example of references. So I have A, B, and C declared in my main program. I called my procedure A, B, and C. And here, A, B, and C is declared again. I have a declaration inside my subroutine here. The names here doesn't have to be the same. You can have different names here, but the order has to be the same. And then you can declare them differently here as well. So here I have declared A star B. So it's two-dimensional A. And using this external subroutine method here, you don't have to specify the second dimension here, or the last dimension of a subroutine, because you can always come to the next by using A here. So you can put the star here if you want. So here I use A here as the size of the B array, and A as size of the C array. There's also a subroutine called or function subroutine, which can have a return type. So the normal subroutine doesn't have a return type, but the function has. So here you declare a type. So for example, real int. There's a function keyword here, the name, same kind of structure with the dummy arguments, declaration. And then if you want to return, you assign the function name to return value, and then you return. So here I have a function f of x, returns a real. And then if I do f equals to cx, it will assign, this is the return value, which will assign to y. Modules is identical to the modules in Python. But here you actually, in Python, you just have a source code file and it's automatically a module. In Python, you need, or in Fortran, you need to declare some additional here in your source code to indicate that this is a module. And the module can contain global data. So you can declare variables in the global that will be exposed to everyone using the module. So you can declare derived data types and associated operations, subprograms, interface blocks. We'll come back to that later. Name this definition as well, that is for I/O operations. And for example, usually you put everything that is related to some kind of task inside a module. So it can be integral arithmetic module, finite elements of a certain type. So it's a way of grouping things together and organizing your code. Syntax is very similar to the program. So you have module, name of the module, specification statement, contains, and then here you have your module subprograms inside the contain section. And module name. So here is a very simple module that just exposes, for example, the selected real kind constants. So I can declare multiple constants. I declare these two constants in my module. And instead of repeating these selected real kind statements in every module or every function, I can just use constants here in my code. And those constants will be available to me in my code here. IK sets and RK. You can also declare variables as private or public. So by default, every variable in module is public. You don't have to declare that. But if you want to hide implementation detail, you don't want some user of a module to change something or modify or rely on a variable inside the module, you can put private here as an attribute. And then it's not possible to access that from outside. And here you can also have a subroutine here inside my module contain section. You can also declare private and public the different functions here. So you can have certain function that is private that's only available inside the module. You can't call it from outside. And you put private here on the function name. So here in this case here, I show how you use it from a main program. You have use trust that makes all the functions, public functions and variables available to you in the program section here. And if you call bar to read, this function is now available to call. So I'll come back to this again. Changing a parameter in the subroutine affects the variable in the calling routine. And that is the reason for this is that makes quicker subroutine calls. But you can also get undesired side effects. So if you have a library that found on the internet you want to use, you call a subroutine with your data, then all of a sudden the subroutine actually uses your variables inside. So after you call, your own variables have been changed. Something you have to look out in the documentation. Yeah, as I said before, the variables in the subroutine doesn't have to have the same names as the calling subroutine, and the last dimension of the left out for arrays. So here I have a bit more complicated thing. So I have subroutine that has an A here, A array, and I have a B array here as well. And A is a two-dimensional array. And having separately compiled subroutines, you need to have a very explicit interface. You need to declare everything that you need to be able to declare the variables coming in. So in this case here, I need to declare A. I need to also declare rows and columns of A, B, and then the elements of B. And then in this here, you can declare your what these represent inside a subroutine. And actually, what I'm doing here is a bit, well, I actually declare A as a one-dimensional array with rows and columns. So there is no, you can actually reinterpret things coming in here. Just as long as the number of elements are the same, you can actually have interpreted values coming in. In this case, I have this is a 4x4, and this is a 16-element one-dimensional array here. And here you can see I assigned values inside this subroutine. So A equals 42. So when it comes out here, the entire array here will be have the value 42. Same thing with this one here. So assignment in here will affect the variables outside here. In this case, this file here is compiled, and this file is compiled separately, and then it's linked together. But that requires you to have, so separate compilation requires you to declare everything you need to be able to declare everything in your subroutine here as well. So there is two versions here. So you have the implicit subroutine interface, separately compiled F95. Compiled does not have all the information, so that's why you need to have all the declarations done in each subroutine file. Explicit here, then you have declare modules. You have you can so the Fortran compiler can see the variable declaration and do some stuff here to enable you to not have to pass all sizes over. So if you use modules or interface declaration, the compiler has all information to use the subroutine interface. I think I have to show an example here as well. So if you use modules or internal subroutines, you can use colon, comma, colon, or colon to declare arrays. So you don't have to explicitly define the sizes of the arrays. And also, so the compiler does all that size handling automatically, which leads to shorter subroutine parameter list. And you can also, in your code, query the sizes of incoming arrays using the size function. So here I have the implicit interface. You have to declare everything here. You have to pass along the sizes over here, row codes, to be able to declare A. So if we then instead go to the module interface, we put this subroutine in a module instead. I use utils here. I can declare my subroutine instead of A rows, comma, cols. You can do my sub A only. And then I declare inside my subroutine that this is a two-dimensional array, but I don't know the size of it, colon, comma, colon, A. And here I can query the size of the array, just like in MATLAB or NumPy. How large is the array? And I can also do this automatically. And that is much easier to call than having the implicit interface. So my recommendation is anytime you do Fortran code, put everything in a module or in a contained section in the main program. Then you get the benefits of using this syntax. If you don't do this, separately compile, you have to declare everything, otherwise it doesn't work. So modules is a good idea. You can also do the same thing if you have a single source code file. If you put your subroutine in the contained section of the main program, you can also use this interface. But it has to be inside a contained section, either in a module or in the main program. There is a way of doing this anyway. Of course, there is always that. So if you want to use an externally compiled subroutine with this declaration here, you need to tell the compiler that I expect the subroutine called my sub for A, and you declare the interface of the subroutine here, not the implementation. And then the compiler knows that my sub for, okay, it has to be, let's use assume shape arrays like this, and I can call it here. If you don't do this, you can't separately compile these files. So this is a significant overhead that you don't want to do. There's also a notion of automatic variables. So these are temporary variables that can be automatically declared for you in subroutines. They're created on the stack and automatically allocated a desired size. They have to fit in the stack. So stack is a special area in the computer for each program that is limited. Has usually you store all the local variables on the stack. It's a very fast way of accessing data. At some point, if you need larger data structure, you need to go on the heap, which is the dynamic memory or in the operating system. So automatic variables. So I have a subroutine here, and I have an A, which is an input argument here. And I want to have a second array here that is the same size as A. Then you can declare something like this. Each dimension size A, 1, so that is the column, the number of rows. The number of columns here is number 2, and then I declare B. B will be automatically allocated by Fortran. So I can use B here. You can the size here. It's only available inside the subroutine. But it can be that you need something that are the same size of A, and then you can just add statements here, having multiple variables that have the same size. So, array features. So what we can do with arrays? Yeah. So one of the ways, or one of the things that is not available in the older versions of Fortran, like Fortran 77, is dynamic memory. So In C and C++, you have the ability to allocate memory on the heap, which is the operating system controlled memory area. Fortran 19 introduced this to Fortran. One of the usage of allocatable arrays is that you can allocate arrays depending on problem size. So if you suppose you have an input file that says that the problem is a certain size, you can inside a Fortran code allocate arrays that have that size that you need. You can define an allocatable array using allocatable attributes, and then you allocate the size, or you declare a variable, but you don't specify the exact size. You only define the number of dimensions. And then you use allocate statement to allocate the array. Several old codes have this work arrays idea, which they implemented their own memory allocation using large arrays. So this kind of replaces that. And when you're done with memory, you can deallocate using deallocate. And when you can have an allocatable array in the subroutine, it will automatically deallocate and return from that subroutine. So how does it look? So here I have dimension colon. You can have that here as well. This is the attribute allocatable. That means that F is an allocatable array. And so if it's two-dimensional, you have colon, comma, colon, allocatable, K. And then you can just allocate F20. Now this variable has 20 elements. Allocate K20 by 20. Now it's 20 by 20. And then when you're done using it, you can deallocate and deallocate for the variables. And also, if you try to use these variables here, you will crash the program. So you need to, don't use them before you have allocated. Another thing that's important is that when you have loops in Fortran, you should try to do the allocation before the loops or after the loop. And also, if you allocate, if you have a long-running code that has an algorithm that repeats, and you do allocate, deallocate, make sure that you always have pairs of these. So you don't have too many allocate, or you don't deallocate after use, then the risk is that the program will grow and will fill up all the memory if you don't make sure that you deallocate out in the loop as well. But it's very costly to do this, so try to do this before going into the looping. Sub-objects, we have touched upon this before. You can use that to create sub-arrays that you can use as input to other functions, subroutines. So here is, I have my two-dimensional array A here. I can do write array here. And I can also do interpret A as a vector here by selecting here a sub object here, sub-array. Column row 1, columns 5 to 10. That will be a two-dimensional array. I have here I put a sub-array here, rows 1 to 5, columns 5 to 10. And I can also do something like this. You can actually create a sub-array with columns 1 and 3, and 2 and 4. And this will be automatically handled for you by Fortran. It could be that some of these statements here will do a copy, because some in certain it will try to avoid doing a copy, but in some time, for example, this 1, 3, 2, 4 will probably be a copied array. So there could be some performance penalties for doing this. I already went into math mode. And I also showed this before. There are also some reduction functions here. If you use all, we return true if all elements are true. So this is also related to a logical array. Any true if any element is true. This maxval and minval. If you want to calculate max value of an array, you can use maxval. Minval, same thing. There's product, calculate the product of all elements in the field. Same thing with sum here, sum all the elements in the field. So look like this. So this is product. So this is A, and then we have product, sum, max, and min. There is also information routines here. So if you have an array, you can query the lower bound of the array, upper index of an array, shape. So this is returns the shape array in rows and columns, and also the size of the matrix in specific dimension, which we used before. So now we have gone through most of the variables, data type, conditional statements. Now we want to be able to write to the screen or read from the screen, also to files and read from files. So reading and writing is the same. It's Python. We use read and write statements. One row for each read-write statement. So read and write will write a single row and read a single row. So it's not as flexible as in Python. The first parameter determines where to read and write. So when reading for standard input and writing to standard output, you can use a star as the first parameter. That will write to the screen or read from the keyboard. Fortran will automatically convert text in a file to type variable values. So if you read values in a certain format from a text, it will automatically convert. So in Python, you didn't have that. In Fortran, we'll do some of this for you automatically. You can read several variables in a single statement. You separate them by commas. And you can also do an implicit loop inside a single read statement as well to read multiple values. So here you have a read statement. In this case, read from star. That means that I read from the keyboard this time. The second parameter here is the format. We don't care about that. So this will read 8 floating point values from the keyboard. So I have to specify values. They can be value and space, value, space, value, space. And when you press, if you have all of these and press enter, it will continue to the next line. You can also simplify this. So you can do this, use this list apprehension like in Python. So in this case, you can do AI, I equal 1 to 8. This is equivalent to this statement here. So they can read 8 values from the keyboard. You can do the same thing for writing. So write star, write to standard output. Star here, I don't care about format. If I do a star here, it will print out with the highest precision output. So you get really long output when you have floating points. There's also a new statement called print star. If you, it's very small here. Yeah, print star and then a comma, and then you can print out to standard output directly. You don't have to specify any format. So this is the format statement in print star, but it will always go to standard output. So the second parameter of write statement defines the output format. Star is default. And as in Python, you use format code to define how to print out the statements. So we have different codes. A, that is a character string with the width n. So that is used for, and here comes a certain number of spaces. In is an integer with the width n. J is a floating point value with width m and n decimals. You can also repeat character codes in the format code. So for example, this should be an I6, I5. That means I will print out 6 integers with the width of 5. And you have to have the parentheses here inside your format strings. So how can this look? So here are an array of 3 elements, floating point, and 4 integers. If I want to print them out in a nice way, I can do this using format coding, but to just illustrate the sizes here, I have just done a lot of strings with the same format. So 3A8, that means I have 3 strings with the width 8, 4 strings with the width 5. Just print out is just have a header with compare. But then I want to print out 3 floating point values with width 8, so 8 characters and 3 decimals, 4 integers with the width of 5. Running this will produce something like this. So you can see here that one here, the field width of the first one here is 1, 2, 3, 4, 5, 6, 7, 8. So 8 here as well, 8 here as well. And then there's 5 here, 5, 5, 5. So by default, there are floating points are left justified, integers are right justified. So unfortunately, the format strings are static strings, but it's possible to handle. So, if, for example, if you have a array that you don't know the size of and you want to print that, you can generate this format code dynamically. And just to show how this works here, it's a trick that we can use. So we didn't declare a format string here. I have 255 here. You can have different sizes of that. So I have an array here. I query the rows and columns, and I create here write format here. So instead of writing to standard output, I write to my string. So this doesn't have to be a file or other unit. You can have a string here. And here I say I want the format code with single character, 1 single integer, 1 single character. And then I write out here. So I have a single character. This is the parenthesis. I have my single integer columns here. And then I add J83 here on top of it. So now my format here will contain this the string that is determined by this number of columns in my array. And then I can use string format here to print out my array here and get the correct number of floating point values correctly. As a trick, you can be useful to know that this is possible to do. So reading and writing 2 files. So read and write data file, you have to associate a file with a file unit. So in Python, you created a file object which you used to read and write. In Fortran, you instead associate the file with a unit number, an integer. So to be able to do that, you first have to be open. So go to Python to create an association with a file name to a unit number. And also in the open statement, you determine if you should read or write to the file. So there are 3 modes of operation of files. There are text IO, which I will explain now. There are something called nameless IO, which text files with named variable array variables, which is similar to the JSON format of Python. And you can also write binary files, which basically takes the binary bitmaps of the variables and writes them to disk directly. And when you're done, as in Python, you need to close the files. Otherwise, there is risk of having some extra stuff on the. You can get corruption if you don't do that. Opening a file. So usually when I do file operations Fortran, I declare constants for my files. So in this case, I have my input file has the unit 15, out file 16. Then this can be any numbers. You can put 17, 42, whatever it is. Just they have to be unique for each file you want to use. So I use open, and then I specify which unit in file, the file name, access here, text file mode. I want to access them sequentially, and action here equals to read because I want to read from the file. Then I can use read, and then I specify my unit here in my in file, and then I read my data here. I close my file. Now I want to write for open. I open my output file here. Access sequential, action write, and then I use write out file here in my operations. Finally, close my out file here. So this is how you write files in Fortran. Reading from keyboard and is done by this. So start here. Read statement means reading from keyboard. There are predefined unit values already from 50s. The 5 here means keyboard, and it has been done since way history. And so this is a reading here. And at 5 you do this here. Other way around, if you want to write here, keyboard. So this 6 here is the standard output, also equivalent to star. I would recommend not using 6, but you should know that 6 is a magic number that you shouldn't use for file I/O. So 5 and 6 are reserved, but star is better to use in your code to write out the screen. So I will skip that. We'll do that on Thursday. So any questions now? I will just pause here.